Lesson 2.6 takes us away from graphing and looking at transformations to comparing two different types of functions in a variety of ways. We're going to add, subtract, multiply, and divide. We're going to find compositions of functions and apply them in real-life problems. Arithmetic combinations of functions, when you have two different functions, you can add, subtract, multiply, and divide them. Now that shouldn't seem too difficult for us to kind of work through, so watch how we set these up. To find the sum of two functions, f plus g of x, notice we actually kind of distribute the f and g to both parts. So you take whatever one function is and literally just add it to the other function. It's really straightforward. The difference of two functions, f minus g of x, would be f of x minus g of x. This one we have to pay a little bit closer attention to that second part. Make sure you subtract everything for g of x, so subtract all parts. Sometimes it's nice to distribute the subtraction sign in and then go ahead and combine any like terms. When f and g are side by side with no plus or minus in between them, it just means we multiply them together. So we're going to take the function for f of x and the function for g of x and simply multiply them. Now none of this should seem new to you when you're working with grouping functions together. The only one that'll be sort of particular is the quotient function. Anytime you have a fraction, notice we have g of x in the denominator. This brings us back to our domain back in chapter 2a. Remember, the denominator can't equal 0, so we may have to add a domain rule when we have quotients. So let's see what we're talking about down below. Given f of x equals 2x plus 1 and g of x equals x squared plus 2x plus minus 1, find f plus g of x. Then evaluate the sum when x equals 3. So we have two parts to this. The first thing we're going to do is f plus g of x. So what that means is if we're adding the two functions together, we're going to just define that definition, f of x plus g of x. Now up above it says f of x equals 2x plus 1, so I'm literally just going to write 2x plus 1 in place of f of x, plus g of x, which is x squared plus 2x minus 1. All we're going to do, everybody, is just combine like terms. We have an x squared, I'm going to cancel that one out. We have 2x and another 2x, so that would be plus 4x, and then they cancel out. We have plus 1, minus 1, and they already cancel out. So f plus g of x equals x squared plus 4x. That's the first part of our answer. It says then evaluate when x equals 3. So if we find f plus g of 3, what that means is we're just going to plug in 3 for each of the x's and simplify. We would have 3 squared plus 4 times 3. That would be 3 squared is 9, 4 times 3 is 12, and 9 plus 12 is equal to 21. There's our second answer. For example B, it says find f minus g of x, then evaluate the difference when x is 2. The first thing you want to do is take whatever's in the parenthesis and expand it. So f minus g of x just means the first function minus the second function. And again, that should seem to be pretty reasonable. The first function is 2x plus 1. But here's where we have to be particular. If we subtract g of x, I'm just making that one a little, well, kind of clear. When we subtract g of x, we have to put that in parentheses. X squared plus 2x minus 1. And it's important to note we need to distribute that negative to all of those parts before we combine any like terms. This would give us our 2x plus 1 for the f of x, and then minus times x squared, minus times positive 2x, but then watch this, minus times negative 1 becomes plus 1. And now combine like terms, we have negative x squared this time for that first part, and now the positive 2x and the minus 2x already cancel out. and 1 plus 1 is 2. So this is our composite, or our difference for f minus g of x. Then we have to go back and plug in f of 2, and I am so out of room right now. So if I plug in f minus g, oh boy, I try to get that to fit here, of 2. I'm just going to slide my screen over here for a second. There we go. That would be negative 2 squared plus 2. Now think order of operations. 2 squared is 4, but the negative that's out in front makes that negative 4. And if you add negative 4 plus 2, we get a result of negative 2 when x equals 2 for the difference f minus g of x. Here's another specific function. Given f of x equals x squared and g of x equals x minus 3, find f times g of x, then evaluate the product when x equals 4. If we expand that product first, fg of x, that just means the first function times the second one. The first function is x squared times, I'm just going to put that in parentheses, x minus 3. To find this product, we have to distribute the x squared into both of our terms. And this would give us x squared times x, that bumps up to x cubed, and then minus x squared times 3 is just 3x squared. There's our product. Pretty straightforward. Now evaluate the product when x equals 4. So we have to find fg of 4. That means we're going to take 4 cubed minus 3 times 4 squared. Well, 4 cubed, 4 times 4 times 4 is 64. Minus 4 squared is 16, and 3 times 16 is 48. If we take 64 minus 48, we get 16. So f times g of 4 equals 16. For the last pair, given f of x equals x plus 3 and g of x equals the square root of x, find f divided by g of x and state the domain. So notice we have to state a domain here because we're working with a fraction. Then evaluate the quotient when x equals positive 9 and when x equals negative 9. All right, so again, the first thing we're going to do is expand that first definition. The f variable, or the f function, is in the numerator, so that's just f of x divided by g of x. F of x is x plus 3, and g of x is square root of x. There's nothing that cancels out or simplifies here, so I'm just going to write does not simplify. If it did, we'd have to try to break things down, but in this case, that's as good as it's going to get. But our domain, though, there's a couple of things happening here. We know that square roots can't equal or can't be negative, but the denominator can't equal 0. So what we have to state for this one is that the square root of x has to be greater than or equal to 0, but the denominator, oh, this is tricky, can't equal 0. So now instead of saying the equal part, we're just going to have to say then that x has to be just greater than 0 in order for both domains to be true. So this is our domain. X has to be greater than 0. All right, so we have our function, we have our domain. Let's evaluate when x equals positive 9 and when x equals negative 9. So we're going to do f divided by g of 9. That means I'm going to plug in 9 in the numerator and 9 in the denominator. So we'll have 9 plus 3 divided by the square root of 9. Well, in the numerator, 9 plus 3 is 12. In the denominator, the square of 9 is positive 3. And 12 divided by 3 is equal to 4. All right, easy enough. Let's try the next one. For the next one, we're going to plug in negative 9. So f divided by g of negative 9. Negative 9 plus 3 in the numerator over the square root of negative 9 in the denominator. Negative 9 plus 3 is negative 6. But we run into a roadblock here. Did anybody catch that? The square root of negative 9 is not possible. It's not a real solution. And if you think about x equaling negative 9, that doesn't hold true for our domain. So it's not true for the domain. So there's no solution for that second part, or not possible. So that's why it's important to have our domain listed for things like fractions and square roots in order for us to know what numbers we can plug in to make sure they work or not. And that's all the further I want us to go today. So make sure to show me your notes when you're complete, and then we will finish the rest of 2.6 tomorrow.